this video, we will discuss dimensional analysis, including the concepts of physical quantities, dimensions, and units. A physical quantity is a property of a material or system that can be quantified by measurement, for example, length, time, and mass. A dimension is the measure of a physical quantity without explicit numerical values, and each physical quantity has only one dimension. A unit is a standard for measurement for a physical quantity. It is a way to assign a number to a dimension. A physical quantity can have multiple different units of measurement. For example, we can have the SI unit, which is the modern metric system, the CGS system that is based on centimeters, grams, and seconds, as well as US customary system, which is based on foot, pound mass, and seconds. It would be ideal to use the SI system in our daily calculations, but in actual work, what we usually encounter would be the US customary systems. So it will be advisable to learn both systems. In using different units to describe physical quantities, it is important to know the concept of dimensional homogeneity. The first rule states that only physical quantities having the same dimension can be compared, equated, added, or subtracted. For example, $3 is more than $2, which is comparable because they all have the dimension of currency. 1,000 gram can be equated with 1 kilogram because they all have the same dimension of mass. As another example, we can subtract 26 kilojoules by 500 joules because they all have the same dimension of energy. But we need to convert the units to the same unit in order to make the subtraction. So we can make it as 26 kilojoules minus 0.5 kilojoules. And then we can subtract the numerical values having the same unit of kilojoules. We have 25.5 kilojoules. As the result of the first rule, any equation or inequality must have the same dimensions on its left and the right side. Using this rule, we can look at the units of different variables in an equation. For example, we can determine the unit of ideal gas constant that should be used in the ideal gas law. We have PV is equal to nRT, so that means we can convert R is equal to PV divided by NT. So the units should be 1 kilopascal times the units of volume, which is liters, divided by mole times the unit of temperature. For temperature, we should always use absolute temperature instead of relative temperature of Celsius. So we convert the relative 25 Celsius to 298.15 Kelvin. So then we have the unit of temperature. If we look up the table of ideal gas constant, then we should have R should be equal to 8.314 kilopascal times liters divided by mole times Kelvin. There is another rule that dimensional homogeneity requires, and that is that the physical quantities with different dimensions can only be multiplied or divided. They cannot be added or subtracted. For example, we couldn't really add 15 centimeters with 5 kilograms because they have different dimension, one with the dimension of length and one with the dimension of mass. But what we can do is to multiply 3 newtons by 4 meters, and that gives us 12 newton meters. We can also divide 110 miles with 2 hours, and that gives us 55 miles per hour. We can also divide 12 grams with 3 grams, and that should give us 4. One thing to caution about is that whenever we see the same unit, say grams here, we should be asking grams of what? If say we have 12 grams of A divided by 3 grams of A, then this indeed is a dimensionless 4. But instead, if we actually have 12 grams of A divided by, say, 3 grams of B, then we are arriving at 4 with the units of grams A divided by grams B. They cannot really be cancelled out. Therefore, whenever we see with the same unit dividing by each other, we should be asking what they are actually representing. Now let's dive deeper into the systems of units. First, we define 7 base units that make up all other units, that is from mass in kilograms, length in meters, time in seconds, temperature in Kelvin, electrical current in ampere, light intensity in candela, and amount of substance in moles. Each of these base dimensions will be assigned the symbols of mass with m, length with L, time with lowercase t, temperature with uppercase T, electrical current with I, light intensity with J, and amount of substance with N. You might see the symbol be different elsewhere. From these base units, we can have multiple units, which are units defined as multiples or fractions of base unit. For example, 1 gram is a multiple unit of kilogram, where 1 gram is equal to 10 to the minus third kilogram. As another example, 100 centimeters is equal to 1 meter. There are many common unit prefixes. For example, nano stands for 10 to the minus 9th, micro stands for 10 to the minus 6th, milli stands for 10 to the minus 3rd, centi 10 to the minus 2nd, deci 10 to the minus 1, and kilo is 10 to the 3rd, mega 10 to the 6th, giga is 10 to the 9th, Tera 10 to the 12th, peta is 10 to the 15th. And an interesting one is Google, which is 10 to the 100, and this inspired the name of Google because they typed the name wrong. We can also have more complex derived units that are obtained in one of 2 ways. The first way is to have compound units, which are units obtained by multiplying or dividing base units or multiple units. And those, for example, can be centimeter squares, miles per hour, or grams per second. We can also have equivalent units, which are defined by equivalence of compound units. For example, 1 kilograms meters per second square is defined as 1 Newton, and 32.174 pound mass times feet per second square is defined as 1 pound force. Newton and pound force are examples of equivalent units. Now let's look at the dimensions of physical quantities. For example, velocity, v, is equal to the distance divided by time. And it should have the dimension, and this is the symbol for denoting dimensions, of L, which is the length, divided by t, which is time. And an SI unit, velocity can have a unit of meters per second. Angle is an interesting one because we know the angle should have units of either radians or degrees, but it is dimensionless. Angular velocity is angle divided by time, and it should have a dimension of dimensionless 1 divided by time. And the units would be radians per second or degrees per second. Acceleration a is velocity divided by time, so it should have a dimension of length per time divided by time again, so time squared. It should have a unit of, say, meters per second squared. Force is equal to mass times acceleration, and it should have the dimension of mass times the dimension of acceleration, which is length divided by time squared. It should have a unit of kilograms times meters per second squared, and usually we define that as newtons. Work can be written as the force times some distance, say x, and therefore it should have a dimension of force multiplied by length, so that will be L squared. And it should have a unit of newtons times, say, meters. Energy, for example, let's say kinetic energy, can be expressed as 1/2 mv squared. Then it should have the dimension of mass times velocity squared, which is L divided by t squared. And it have the same dimension as work. And the unit of energy can be kilograms times meter squared divided by time squared, so second squared. And when we define that as joules. Power is work done per unit time, and it should have a dimension of work, which is mass times length squared divided by time squared, and then divided by time, so time to the third. So the unit of power would be joules per second, and we define that as watts. Pressure is force per unit area, and it should have a dimension of force, which is mass times length divided by time squared, divided by the dimension of area, which is length squared. So finally, we should have mass divided by p squared times length. The dimension for pressure would be Newton divided by meter squared, and we define that as Pascal. Next, we can look at concentrations. Concentration is a quantity that is usually normalized by volume. For example, we can have mass concentration, or commonly called density. Rho is equal to mass divided by volume, and it has a dimension of mass divided by length cube. Density can commonly have a unit of kilograms per meter cube. Number concentration is the number of substance per unit volume, and that should have a dimension of amount of substance divided by the volume, which have a dimension of length cube. It should have a unit of the number of substance per meter cube. Molar concentration, or commonly called molarity, is the number of moles per unit volume, and the unit is also amount of substance divided by length cube, and it would have a unit of moles per meter cube. Note that number concentration and molar concentration have the same dimension, they just have different units. One is expressed in the absolute number of substances, and one is expressed in the units of moles. For fractions, we can have mole fractions, for example, number of moles of A divided by a number of total moles, and it would have a dimension of amount of substance divided by amount of substance. But here we should always exercise caution in the units because we might be concerned of the moles of A divided by the total moles, and you can't really cancel those units out. For mass fraction, we could have mass of A divided by the total mass, and it has dimension of mass over mass. And again, we should distinguish, say, grams of A with grams of total. For volume fraction, we could have volume of A divided by the total volume, and that has a dimension of length cube over length cube. And again, we distinguish, say, meter cube of A divided by meter cube of the total mixture. Flow rates are quantities that are normalized by time. For volumetric flow rate, it is the volume over time, and it should have a dimension of length cube over time. And for example, it could have a unit of meter cube per second. Mass flow rate is the mass that has been flown over unit time. And for mass, we can also convert it as the density times the volume over time. So it is equal to density multiplied by the volumetric flow rate. And this has a dimension of mass over time, and could have a unit of, say, kilograms per second. For momentum flow rate, note that momentum is a vector, so let's be concerned of, say, one component, x component. Then the momentum flow rate in the x component is momentum in the x direction over time. And the momentum can be written as the mass times velocity in the x direction over time. Then it should have a dimension of mass times the length divided by time, and then divided by time again, so time squared. And it could have a unit of kilograms times meter divided by second squared. The kinetic energy flow rate is equal to the kinetic energy being flown per unit time, and that has a dimension of energy, which is mass times length squared divided by time square, and then divided by time, so we have a time cube. And it could have a unit of joules per second. There is another way to view these flow rate quantities, and that is in the perspective of substance that is actually being flown through a pipe. For example, here I have a third-dimensional pipe in x, y, and z. And the flow is flowing in the x direction, perpendicular to the surface of delta y and delta z. And the side of delta x can be written as the velocity in the x direction times the time that it has elapsed. If we want to calculate the volumetric flow rate, which is the volume over time, then we should have the volume, which is delta x times delta y times delta z over the time that it has elapsed. And we can note that delta x divided by time is actually the velocity in the x direction. So we can rewrite that as v of x multiplied by delta y times delta z. And we can rewrite the mass flow rate as equal to the density times the volumetric flow rate. And that will be equal to the volumetric flow rate, which is Vx delta y delta z times the density. The momentum flow rate in the x direction can be written as the mass times velocity in the x direction over time, which is the mass flow rate times the velocity in the x direction. And we already have the mass flow rate, which is rho times v of x times delta y times delta z, and we multiply that with v of x. We can rewrite the kinetic energy flow rate as 1/2 mv squared in the x direction divided by the time. And note that mass divided by time is the mass flow rate and multiplied by v of x squared. And we already know the mass flow rate, and so we can rewrite that as 1/2 rho vx delta y delta z multiplied by v of x squared. We do this type of extra conversion because sometimes we're interested in, instead of the flow rates, we're more interested in the flux, which are normalized by both time and area. And the area is orthogonal to the direction of transport. For example, in this case, if we're interested in the transport in the x direction, then we're looking at the area that is perpendicular to the x direction defined by delta y and delta z. So the mass flux is the mass flow rate divided by the area. And the mass flow rate we already know is rho of v of x delta y delta z. And say if we're looking at the x direction, the area orthogonal to x direction is defined by delta y and delta z. And they cancel out, so the mass flux is defined as rho vx. The momentum flux in the x direction then is defined as rho vx delta y delta z times vx divided by the area, which is delta y delta z. The area cancels out, and leaving us with rho vx times vx. Note that one of the vx is coming from the mass flux, and the other vx is coming from the momentum, which is m times v. And the kinetic energy flux, so Ke flow rate divided by the area, can be written as 1/2 rho times Vx delta y delta z Vx squared divided by the area, in this case delta y delta z. They cancel out and leaving as 1/2 rho Vx times Vx squared. Again, you can view rho times Vx as the mass flow rate divided by the area, so the mass flux. So you can basically see this as 1/2 mass times velocity squared. For the dimension of derivatives, it is dependent on the denominator. For example, if I take the derivative with respect to x of something, then this derivative operator has a dimension of 1/length. If I'm taking the derivative with respect to time of something, then this derivative operator has a dimension of 1/time. For example, if I'm looking at the change in temperature with respect to length, then this should have a dimension of temperature over length. If I'm looking at the second derivative of length with respect to time, then this should have a dimension of length divided by time squared. For integrals, the dimension is dependent on the differential. For example, if I'm integrating with respect to x of something, then this integral operator has a dimension of length. If I'm integrating with respect to some time, then it should have a dimension of time. For example, if I'm integrating the velocity with respect to time, then the dimension should be the dimension of velocity, which is length divided by time, multiplied by the dimension of the differential, which is time. So it gives the dimension of length. This result makes sense because this integral is indeed describing the distance. In this video, we went over the concept of physical quantities, dimensions, and units, and gave several examples for each of them. Having a good grasp of dimension and their units is very important for the study of transport phenomena in future dimensional analysis.